Terrific. All right. Well, our featured speaker today is Nancy Scherich, who's an assistant professor of mathematics at Elon University and generally works at the intersection of algebra and topology, often motivated by problems arising in knot theory. She's also a dancer and choreographer and creates beautifully produced math dance videos, which use dance as a way to communicate and teach higher concepts in mathematics. In the summer of 2017, she won Science Magazine's Dance Your PhD competition with a video about representations of braid groups and has released a number of gorgeous videos since. And so I'm really excited to hear from Nancy. Thank you so much for joining us.
Thank you for inviting me. All right, let me get this situated. So I got two screens going on, so hopefully it's not too confusing. Mm. Wait, now it's not sharing. Oh, what happened? Hold on, sorry. Where did you go? Oh dear, I actually lost my thing. Hold on. Technical difficulties.
Been known to happen.
All right, well, it's not liking me sharing my full screen, so we're just gonna do not the full screen. Okay, so sorry about this, but I think you're gonna see all my side stuff, but it doesn't like me to do the full. So we will do it this way. And if I pull it here, can you still see that? We good?
Yeah,
Okay.
we can see it.
Okay, so sorry, it's kind of funky. All right, so thank you so much for having me. And I want to tell you about how I use my dance videos to explain my research. So I give a lot of outreach talks. I work at a primarily undergraduate institution, and so I'm really interested in getting undergraduates excited about doing math research. And so I give a lot of talks at other primarily undergraduate research institutions. And so yeah, so mostly I make dance videos, and that's kind of what I'll share with you today. But I've done some performative lectures where I've given performances and lectures at the same time. So I'm dancing while teaching mathematics. And that's pretty fun, but it's actually really a lot of work and kind of hard to pull off. So I've veered away from that a little bit. I've also done some live performances that are pretty fun. But I really do like the video aspect because I can reuse them and give lots of talks and sort of share my work with lots of people versus a live performance. Sort of the only people that get to see it are the people who come to the performance. And so you can't really share it as much. So I was just recently an organizer for the iCERM Illustrating Math conference we just had. And while I was there, I gave a talk about sort of my process, about how I make these dance videos. And so I'm not going to talk about that too much today, but I will point you to an article I wrote in the notices last year that kind of talks about my process and lays out sort of the timeline, how long it takes for me to make one of these videos, and what goes into them. So if you'd like to check that out, I'll send you there. Okay, but for today, what I'll kind of do is give you a quick overview of how I give an undergraduate outreach talk using my videos. So I'll kind of tell you how I structure them and how I use my videos in that process. So pretend you're an undergrad right now who's never seen any knot theory, and I'm going to teach you some knot theory. Okay, so I usually start out class or start out a lecture like this where every student has a little pre-tied knot that I put on their desk, and I'll sort of start out teaching them what is the purpose of knot theory. And so I show them this image and say, we're really interested in classifying knots. And really the kind of difficult question that arises is how do you tell if two knots are different or two knots are the same? And so one kind of distinction we'll make is the difference between a knot versus a knot diagram. So knots are supposed to be three-dimensional knots that actually, take up space. But a diagram is how we typically study them and draw them. So that's going to be a two-dimensional drawing of the knot. And our main question is going to be, when are two knot diagrams the same, or when are two knot diagrams different? And this is very similar to the question of when two physical knots are the same or different. So then at this point, I'll tell all the students, okay, so you have a knot on your desk and so does your neighbor. Do you have the same knot as your neighbor? And so the first thing you do is you pick up your knot. And then I yell at everyone. I say, no, don't touch your knot. And then they get all scared. And they're like, wait, what did I do wrong? And I say, wait. If you touch your knot, like if you move it, have you changed the knot? And then they all get like panicked, so it's kind of a fun moment. But anyway, so that leads to a discussion about like, are you allowed to change your knot? Is that an allowable thing to do? And so then we ask, let's start with an easier question. So here are two knots, not very interesting knots, but here are two knots, and are we going to consider them the same? And so clearly they are different shapes, but as a knot, are they the same knot? And the answer to this question really depends on from what perspective are you going to study knot theory, and what perspective are you going to study your knots? And so we can sort of, study knot theory wearing different hats, wearing a geometry hat versus wearing a topology hat versus wearing an algebra hat. And so this first video I'd like to share with you is a video I made to exactly get at this idea that mathematicians can study the same object, but depending on what kind of area of mathematics they're studying it from will determine how they study the object and what properties about the object they will understand. So give me just a second to pull this up. I'm going to share so I'm going to stop sharing real quick. In the chat, I'm going to share a link to this video on YouTube. So if for some reason the sound quality isn't good or my internet's not good, you can pull up the video on your own computer and watch it yourself. And let's go ahead. Okay, and really quick, is sound coming through? Could you hear that? Okay, great. All right, here we go.
Most people understand that science is a broad term describing many different fields of study, like chemistry, biology, and physics. What makes these scientific fields different is not necessarily that they study different objects, but that they use different techniques to study the objects. Just like science, mathematics is also a broad term that describes many different fields of study, like algebra, geometry, and topology, and many others. However, many people don't understand how these mathematical fields are different. So, let's take a closer look at how a geometer, a topologist, and an algebraist study a circle. To a geometer, a circle is made of a rigid material, and it has a perfectly round shape. From this geometric perspective, we can study the curvature of a circle, as well as reflectional and rotational symmetries of a circle. From a topologist's point of view, if you look at a circle from different angles, it no longer looks perfectly round. It might as well be made from a flexible material. From this topological perspective, a circle can take on many different shapes and forms. So we can learn about knotting and braiding of circles. From an algebraic point of view, a circle is a collection of separate points, along with a rule for connecting the points. We can choose different connection rules to describe the same circle. And from this algebraic perspective, the circle can be used to visualize non-standard arithmetics. Although these fields of study are very different, the greatest mathematical discoveries happen when the different fields of mathematics work together.
Learning how to take a pattern.
No, okay, sorry. Let me get back to my slides. Okay, so I made that video mostly to try to explain to my mother that topology was different from topography. Um, but yeah, it's been very handy when I give these talks because it helps give a reference for how I study knot theory and how we're going to talk about studying knots. So if we want to study this this knot called the trefoil, we have to decide from what perspective, what mathematical perspective are we going to study it from? And we can choose, you know, what we want to do. So if we were studying it from a geometric, or so from any perspective, it should be pretty clear that sort of the crossing information is going to be pivotal. What's kind of going to make different knots different from each other is how the strands sort of interleave and cross each other. So from all perspectives, we're going to care about the crossing information. And if we were thinking geometrically, we're going to care kind of about what the knot is made out of in a sense, like how long is the piece of rope that you tied it out of? How thick was the piece of rope? What's the radius? And then from a geometric perspective, once you've tied your knot, it's rigid. Like you can't change it. You shouldn't change it because that's going to change the shape of the knot, right? And so geometry cares about shapes. So from a geometric perspective, knots are going to be very rigid objects. Well, you might say, okay, well, I mean, if I'm looking at this knot that's in my lap, it's not rigid, it's flexible. And so somehow we want to see that knots, you can sort of rearrange them and untangle them. Maybe sometimes you can untangle them to be the unknot, just a loop, or sometimes they're actually truly knotted. And so it might seem like maybe geometry is a bit of a limited perspective to study knot theory. So instead of geometry, we want to study it from a topological perspective. So from this topological perspective, we're still going to care about the crossing information of the knot, but we're not going to really care about like what the knot is made out of. I don't care about the strength, the length of the rope or the radius of the strand. What I really care about is that once the knot is tied, it's very flexible and I can rearrange it and move it around as long as I never cut it. And so from this perspective, we're studying knot theory as a topologist. And so if we want to really encode or understand, sorry, let me zoom out, there we go, how you can do this rearranging, then we get to the Reidemeister moves. And so, you know, I spend a little bit of time when I'm working with this and I'll have students like grab their knot diagram and we'll go through the Reidemeister moves. And so I'll kind of go through this a little quickly, but there are 3 Reidemeister moves. And the first one is when you can add or remove a kink to your strand. The second one is if you poke a strand up and over or back and behind the other one. And the third Reidemeister move is a little bit harder to see, but you can think about it as taking a strand and moving it across a crossing. And so it turns out that 2 knot diagrams are the same if and only if they're related by a finite sequence of these Reidemeister moves. And so let's see an example of that. So here I'm starting with a figure 8 knot and I'm doing a bunch of Reidemeister 2 moves. So I'm taking this strand over here and I'm sort of poking it behind these 2 arcs here. And then I'm doing a Reidemeister 3 move that's happening with this arc here. I'm pushing it behind that crossing and so on. And so you can really rearrange the way your knot might look. And so these are all different knot diagrams for the same knot. And we're just doing Reidemeister moves. And so every diagram here is representing the same knot, even though they are different diagrams. So then let's come back to these 2 knots that we started out with. Well, are these 2 knots the same? And if we wanted to answer that question, like if they were the same, well, then we'd have to show we can find a sequence of Reidemeister moves to take one diagram to the next one. But if they're not the same, then I'd have to prove that there is in no way ever going to be possible to find a sequence of Reidemeister moves to take me from one diagram to the next. And all of a sudden, that's a much harder question. And so what we see is that Reidemeister's theorem, or using the Reidemeister moves, isn't necessarily the best way to tell when knots are different. It's really useful to tell when they're the same, but not necessarily to tell that they're different. And so we want to move to a more complicated way of trying to distinguish knots. And this is where knot theorists use invariance. And so the way an invariant works is you start with your knot diagram and you're going to compute something about your knot. And you're going to compute something that's easier to compare than 2 diagrams. So like I can compare 2 numbers or I can compare 2 polynomials. And that way, if I have one knot and I get a polynomial and one knot and I get a different polynomial, if I can compare that they're different polynomials, then I know that my knots that I started out with are different. All right, so most of the methods that I study of creating these invariants are using sort of an algebraic approach to study our knots. So when we were thinking topologically, we were really thinking about, the motivation of our knot is made up of this flexible rope. And then to create an algebraic perspective of this, what we want to do is sort of encode all of that wiggleness, like the ways that ropes can wiggle, in terms of equations. So I'll go through this next bit a bit quickly as well, but then we start talking about what are braid diagrams and what is sort of the algebra of braids. And so these are two examples of braids with 4 strands. And the one thing I'll point out, in case you haven't seen braids before, is something that's really important about a braided diagram is there's a monotonicity condition. So if you view your strands as like pipes with water in it, the water would be able to flow all the way down and never get stuck or pool up at some point. So all of your pipes are always moving downwards and downwards and downwards. And so then we'll take a little time and go through the algebra of braids. There are these little generating braids that have a single crossing. And the way that you build up larger and larger braids is you stack up these little generating braids. And so we can have an operation on our braid group that's called stacking. And another part that's really cool about this is it gives us a way to write our braids using words, using symbols instead of using diagrams. And this is how we're sort of stepping away from a diagrammatic approach into a more algebraic approach of sort of getting equations. And there's a few different rules. So let me go to this one. So we saw the Reidemeister rules before. And so here's how you might interpret a Reidemeister move in terms of these labels that we have for our crossings. And so if I want to say that these two braids are the same, it gives this algebraic equation that a sigma I, so that's a crossing in the ith position, and then a crossing in the ith plus 1 position, and then a crossing in the ith position is actually the same braid, right? Even it's a different braid, but it can be rearranged into the other one. So that's why we're calling them equal, even though their diagrams look different. So this one has a crossing in the ith position, then in the I plus first position, then in the ith, and then in the I plus first position. So now instead of drawing this picture that says 2 braids are the same, I can now draw this equation. And so we're sort of stepping away from the pictures a little bit. And here's another relation that if your braids are sort of on disjoint strands, then they commute past each other. So this tells you that sigma I and sigma j, you can change their order as long as the difference between I and j is bigger than 1. And if we put all of this together, we get what's called the braid group. And the braid group has generators sigma 1 through sigma n minus 1. So these are going to be all of my little tiny baby braids with the single crossings. And then they satisfy some relations that we saw before. So now I can think totally algebraically about braids using these sorts of equations and writing down words in these symbols and think about these equations as different spellings of different words. Okay, so what do these braids have to do with the knots that I want to understand and ultimately thinking about computing an invariant? Well, a really, really cool theorem is that every knot can be rearranged to be the closure of a braid. And let me show you why this is so cool. All right, so if you have like your knot in your hand, so let me kind of spread it out for you. Hopefully you can see this a little bit. All right, so your knots are going to look kind of crazy like this. You might say, all right, well, to make my knot look like a closure of a braid, the closure is where I connect up the top and the bottom endpoints with kind of this rainbow picture. So you might think about, all right, well, what if I just pull all of my crossings into one little spot and then I can see the rest of my strands as sort of forming that closure. But the issue is if you look at where your knot, like all of the crossings are, it's not going to have this monotonicity condition anymore. So the real sneaky thing about this theorem is that you can actually rearrange your strands of your knot so that the part where all the crossings are has this monotonicity flow. It doesn't have any points where like water could get stuck in the pipes. And so this next video I'd like to show you is an algorithm that achieves Alexander's theorem. So let me go ahead and pop this link in the chat for you again. All right. Oh, and this one I will say, it's kind of a dark video, so if you want to turn up your screen brightness, it will help you see it a little bit better. Okay, so we just watched this video about Alexander's theorem, and so I'll kind of quickly just tell you how I would wrap up a talk. So then I would talk through a little bit of a process of how you would use braid groups to help you compute an invariant using a representation. So you would take your knots and you would go through using that Alexander's theorem process to create the closure of a braid. And so you'd write down what is the braid that you're taking the closure of each of these knots. And then we're going to compute what's called a representation of the braid group. So a representation, we'll talk about that in a second, but it's a way of turning braids into matrices. So the fancy way to talk about a representation is it's a group homomorphism from your braid group into a general linear group. The less fancy way of saying what a representation is it's a process that turns braids into matrices. So we go from knot to a braid to a matrix. And this process of turning a braid into a matrix has to be done very carefully. So saying it's a group homomorphism means that this mapping that we're doing, this way of turning braids into matrices, needs to preserve all of that beautiful structure of braids that we saw before, in particular the multiplicative structure. So if you have a group homomorphism, it has to respect multiplication. So if you take two braids and multiply them, then apply your representation. You have to get the same answer as if you would separately compute the representation of one braid, separately compute the representation of another braid. So here we have two matrices and then multiply them together. You need to get the same answer. So representations are sort of a very careful process that turn braids into matrices, but preserving this multiplicative structure. And so if you have a representation of your braid, so you go knot braid matrix, then from your matrix, you can compute different like mathematical properties. So one of them is you can take a determinant. And so the one I've computed for you here is the Alexander polynomial, which you can get as a determinant from the Burau representation of your braid group. And so here what we've done is we've done a lot of multi-step processes, but we've come up with two different polynomials that are clearly different polynomials. Like those two things, we can compare them, they are different. So the two knots that we start out with must definitely have been different knots. So that question that we posed at the beginning, are these two knots the same? The answer is no, they are not the same because they have different invariants. So the last video I'd like to show you is about representations of the braid group. So this is a video I made to try to talk through this idea of how do you turn a braid into a matrix and what are some properties that we might care about. This video is a little bit longer, it's about 10 minutes. But yeah, so that's kind of the end of the story. And depending on what level of talk I'll give to institutions, I'll go in and talk a little bit more about how you might construct these representations, what goes into them, and what are some other like uses that you have for them. But kind of what I wanted to share with you all today is, we might think about illustrating what we're working on, research wise to other researchers, but also thinking about how you might engage with undergraduates and how you might sort of tell a story with multiple illustrations at different levels, I think has been really helpful for me. And it was kind of accidental. Now that I have kind of this talk prepared, I give it a lot and I think about like, oh, is there an aspect of this talk that maybe I could say better with a video than with a couple of slides? And, to try to build almost a playlist that would tell the whole story. But yeah, I kind of want you to think about how you might, build a repertoire of illustrations that you could use together. And that's been really helpful for me. And I really enjoyed giving these talks. And I apologize that the sound wasn't working so great. But that's all I have for you today. So thank you so much.
Thanks so much, Nancy. That was amazing. Uh, yeah, that was so great. I want to open the floor. We do have a few minutes left for questions. So if anybody has questions, you can post them in the chat and I could bounce them forward, or you can just unmute yourself and ask away. There's also a thread in the Discord for continued conversation. But for now, let's take the next few minutes and take questions, if that's all right with you, Nancy. Martin's got a hand raised.
Yeah, I thank you so much for the wonderful talk. Amazing videos. Definitely going to rewatch those. But I was wondering whether you could expand a bit on what you mentioned last year. So, do you have an example as to where a video was super helpful in explaining a certain object, a certain theorem, a certain something, or where even after you have this amazing video, you still find yourself going back to like more traditional ways of explaining this via slides or drawing?
Well, I think the more ways you can explain it to somebody, the better. So say it in words, say it with a slide, say it with a video, and then say it with words again. I think is a good way of communicating. But I don't know that I have, let's see, a specific example. I mean, I will say the video I made about what's the difference between algebra, geometry, and topology, that I think the video says it better than just saying it in words to someone. And partly because I mean, I guess I could just say the narrative of the video, but sort of making a comparison to something people already understand, that there are different fields of science that can study the same thing. Like, a biologist, a chemist, and a physicist can all study water, but what they're going to notice about the water is super different. And so that mathematicians sort of do the same thing, and that's why we need these different fields of mathematics. We're going to notice very different ideas. So yeah, so I suppose you could also say it in words, but the videos better at it, I think.
Thank you.
Yeah, I thought the unpeeling of the circle from the hula hoop was really effective. Just like that moment was amazing.
Thanks. Yeah, so low tech, right? It's just fabric wrapped around a hula hoop.
Yeah.
Could you maybe say a word or two about how long the planning takes? Like there's obviously a lot of thought. I also noticed in particular the rigid circle being turned into an exercise band, and I was like, oh, that's great. But so
Yeah.
please.
So it usually takes me about a year start to finish to make a video. And part of it is I'm just really slow. I'm sure like if I was doing this full time, I could probably do it a lot faster. But the sort of kernel of the idea will happen just randomly at some time. Like I was in a dance class when I came up with the idea for the Alexander's theorem video. And then when I have the key idea, I draw out some storyboards for it and figure out like what are the kinds of props I would need and what needs to be said. And then then I would figure out what does the music need to look like, and sort of there's a long journey of figuring out what are all the pieces that will have to come together before I actually film it. So the filming doesn't take very long, because they're, you know, pretty short videos, but you know, the filming takes, I don't know, a week, 2 weeks. But yeah, determining the props is a really difficult part of the process. So like, you know, just that the idea of, oh, if I just wrap some fabric around a hula hoop and pull it off, it's really effective. Or versus like the Alexander theorem video, it took a really long time to decide what to make the knot out of. And I'm really glad I decided to go with the LED lights, because it showed the flow really well. But yeah, the props take a while to figure out. Mhm.
Are you working on any new videos?
Yes, slowly. So I have two ideas. I have one that I mentioned at the Illustrating Math conference we just had, where there's a really big technical hurdle that I have not figured out. And so as soon as I can figure that out, then I will jump in to start filming. But it's a big technical hurdle. So I think I'm going to be sitting on that idea for maybe a couple years. But I have a smaller video that I'm hoping to film in the spring, that's based off of some of Carl Schaefer's work. So Carl was at the conference, if you know him. He's also a math dancer, but he does these really beautiful string figures. We have groups of people holding ropes, and you can make all the polyhedra by like pulling pieces of the rope around, and it's really, really cool. So I was thinking I might make a video about that, where the rope is an LED rope. And so it's a very dark video, but you just see these shapes coming into place and just some like light on people's faces. And so that one would be less educational and just more of a really cool dance that's math. But that's kind of.
Yeah, I got to participate in that process last month at iSermon. It was a lot of fun.
Mm-hmm.
Surprising how those shapes just suddenly emerge.
Yep. Yep.
Amazing. Well, we're hitting noon, so unless there's other burning questions, maybe we can kind of shepherd folks to Discord to continue. Keep an eye out for this on YouTube, and for the seminar to continue through the fall series. Thanks so much, Nancy. Again, let's give her a round of applause for kicking off the fall. That was awesome. Thank you so much.
Woo!
Woo.
Yes, thanks everybody again for coming, and we'll see you next month. I will stop the recording and end the call. Take care, everybody.